Swayam Prabha. Digital India. Educated India.
Okay, welcome back. So, you know, if you and there are others, Autodyne. I think one of you was mentioning NISA. I haven't used that myself. I've developed material models for explicit, Abacus explicit. You can also develop your own material models using what is known as VUMAT or UMAT in Abacus. Similarly, LS-DYNA also. So, if you don't like any of the material, there are lots of PhDs that are produced just to develop one material model and run it. Some of those concrete material models you use, those are probably developments over a few years, and then validations, presentations and conferences and all that. So, they have spent tremendous amount of time, but there's still a lot of variability in the results that you get. So, there are in finite elements itself, FEM, there are broadly three different categories: Lagrangian simulations, and then you have the Eulerian simulations, Lagrangian Eulerian simulations, and then you have, see, a Lagrangian simulation, for example, this is your structure. You will model this is a Lagrangian structure, solid structure, and then you will have, let us say, your TNT somewhere here. What it does is it will apply the pressures, it will calculate the pressures on this structure. These are blast pressures. These are using the, let us say, the Friedlander equation. Internally, they will have methodologies by which the load gets converted. You will specify the distance, the location, heights and all that, and once you specify that, a simple analytical expression converts, applies the load, solves it, right. In Eulerian Lagrangian type simulations, you might have, let us say, you can model the structure here, and this would be air. So, air is modeled as an Eulerian, and then the structure is modeled as a Lagrangian. And I have done a couple of types. You can model, let us say, a volume. This is your TNT. You can model the explosion, and then you see the propagation, and then automatically it will apply. You can see the pressure displacement. So, the pressures are calculated using the Eulerian, or you can have what is known as multi-material ALE. This is, it is called arbitrary Eulerian Lagrangian formulation. So, you have ALE where you can have the structure itself, and then this is your air mesh, and then you can have a TNT mesh somewhere here. And so, in this, the material TNT, this is air and TNT both. As the TNT explodes, these kinds of, the properties of TNT and air are different. So, they propagate into these. So, those are multi-material ALE formulations, you can use that. Other types of simulations, now the problem with ALE is very time consuming simulations. So, if you want to simulate even 1 meter, 2 meter air, and you want to, it is also mesh dependent. So, if you are having a mesh size something like this versus a mesh size something like this, right? The pressures, so if you are comparing the pressures versus time, you will perhaps get, this is for coarse, and for fine you might get something like this, right? I am just giving some examples. So, the pressure distributions are different for different cases. So, you will have to see which mesh size works well. So, we do what in all, most people ask this question, have you done a mesh sensitivity analysis? To check for an ideal mesh size. Problems with concrete and the mesh size, it also it depends on many things. It actually depends on even your Lagrangian mesh sizes. Mesh sizes also depend on the type of material used. So, I have found, for instance, that for concrete, for the simulations we had, the 1-inch mesh size simulated the experiments best compared to even half an inch. You would think that as the mesh sizes keep decreasing, your simulations converge, right? It should converge, same deflections. Doesn't happen because concrete is a complex material. Or even for that matter, except aluminum and steel, and which are homogeneous materials, composites and others fall into the range, complex materials. The mesh size also depends on the type of material for that particular simulation. You take some other experiments, maybe the mesh size is a little different. So, we've gone with recommendations of mesh sizes for this type of, it depends on the material behavior as well. They are all intertwined. Another option you can do is if you have a very long structure. Let us say if this is 10 meters and you are simulating a structure here. Now, you start putting a very fine mesh of air. If you are doing 1 millimeter or 2 millimeter meshes, imagine this is 1000, 2000, right, 10,000 multiplied by whatever height you simulate. All that really, you can give a simulation today, take a vacation, come back and then your simulation will be ready, right. If it does not work, tell your professor another vacation time, come back, right. But what you can do then is, you can use a smaller, this is your structure. So, this surface, your TNT is still here. Up to here it will use Friedlander equations. So, probably up to 8 or 9 meters you are making some assumptions there, you can check 8 or 9 meters you can use, and then from here to here you can use air mesh. So, you are combining ALE, this is not ALE, this is ALE plus your Lagrangian simulation. So, those are CEL, combined Eulerian, see, he knows better, combined Eulerian. There are other techniques too. So, people spend a lot of time developing formulations. LS Dyna, that is the nice part of it. You contribute something, you validate it, you publish it, and you ask them, they will incorporate your model into their database. That is how contributions go in there. Then there is structured ALE, so many different, I do not know if any of you have you used that? Yes. So, that is another thing I have tried, I have used. So, the complexities are even in simulation itself, right. We talked of the mesh. If you are having a complex structure which has got sharp corners or which has got many variations, then you start getting into the mesh quality. So, mesh quality, people invest a lot of money in, there are companies that just do a lot of nothing but sell meshing software. They charge a lot of money for it, especially for commercial purposes. Research purposes, you might get it a little cheaper. So that the quality of mesh is very, very important in certain types of applications. So just to give you a flavor, how do I, Raghav, how do I get to any desk? Just what? This one? Yeah, you can, it's come up, right? So let me open a file. This is one of the, this is using LS-DYNA, and you're going to get a experience of it. Which one? So we looked at seismic, this is a column simulation, and we looked at seismic detailing, several types of detailing. So here if you see series A, like that, series B with erosion, without erosion. Erosion is something, one of you was asking that they get a very common error called negative Jacobian. So negative Jacobian occurs. What is a negative Jacobian? It basically represents the volume divided by the volume when the determinant goes to 0, or then your or negative volumes, they just fold into each other, right? Then the simulation does not proceed. And it could happen. You could have 1,000 elements, and if one element gives you a negative Jacobian, program doesn't ignore it, it continues. Then we do erosion, which means, okay, we say that we have an erosion criteria. If the strain in that element goes to 0.1, let's say, or 1% or 5%, whatever, remove that element. When you remove the element, you are removing the mass also. So removing the mass actually changes, you're inherently changing structural properties or the response you are. So in a finer mesh, maybe erosions that could, you're not affecting it so much. So you have to keep track of what is known as inertial forces. So you have to track your actual forces, inertial forces, damping forces, and any other forces, thermal forces if they are, and or the energies, and see what percentage of each they are. And if your inertial forces percentage is low, then you can say, okay, erosion has not mattered. So apart from just meshes, right? If you see, for example, if I take out concrete, you see the steel, you create all these meshes. You have to, structural simulation with LS-DYNA or Abacus is, I mean, compared to other structural analysis programs, this is not, you're not a beam, you're not using beam elements and column or beam elements or that type, right? Here you're using actual finite elements. So you have to simulate each of these. As I've used beam for some reason, but these are all axially loaded elements, and you have to simulate each one of them. And so starts with your meshing. Then if you take out the steel 1, steel 2, so you have to create all these. So that complexities are there. And then once you do that, now then you define, how many of you have never used finite elements here? So everybody's used it. You have never, yeah, don't feel shy about saying if you have not used 1, 2, 3, okay. So the others, you can just listen to it, or if you have questions. So you have to have your boundary conditions wherever they are. Then you have to define, there are many things. Main thing is, if you see the load, let's go to the keyword file. Okay. So in LS-DYNA, if you, so boundary, then constraint, these constraint conditions you have to define. Here what we call a CLIS is, you have the interface between the steel and concrete. One way is to tie them to the nodes, but then you're not going to do that. So you can mesh them independently and then do a constraint so that they are not, there's no bond failure. There are bond failure laws models also. You can say, okay, there is a bond slip relationship between the steel and concrete. People have worked on that. Maybe there's a PhD or somebody who's spent time in developing bond slip laws, and you can incorporate bond slip laws in this also. Contact conditions are very important, especially when you're applying pressures. Then there's a lot of control cards in a typical hourglassing is another phenomenon, especially when you use integration technique, numerical integration techniques. There is something called full integration and reduced integration techniques. So in a numerical integration technique, they'll take an element, instead of integrating, they have coefficients for, let's say, 4 points, and then multiply, and just it's a mathematical multiplication. But when you do reduced integrations of 4, you take 1, because in explicit analysis, explicit is time stepping, implicit is the other way. In explicit, when you do time stepping, right, then you have to, you don't want to go 4 points, you want to reduce it, and then, but then hourglassing can occur. It changes shape, but the whole property itself has not changed. Artificially, it does. So you have to have a hourglass type. Then the time steps, you were asking about the time step. I'm trying to see if it opens up. So there are controls here from you can either give it or you can specify yourself. If you don't like what it gives, you force it to something higher and see what happens. Then the thing I wanted to is, there's a lot of definitions. The curves are needed. We won't get into that. Let me give you a flavor of what the hourglassing is. This is hourglass ID. There are different types of hourglassing. It tells you for different types of elements what are the viscous forms for hourglassing controls. You see how many parameters are there? How do I know, which one is most sensitive? Even I'm not even getting into the material one. I go in a very systematic manner, fix everything. I'm sure all of you who work in this area do that. So this is what I was talking about in the Lagrangian formulation. You can specify the weight, the location, and here this is conversion factors, and be done. It's a very simple formulation. What it does is it will apply calculated pressures. Then the material for steel, most people use this. This is where your plasticity comes into play. But concrete, if you look at, I've compared 3 different models. I've looked at Winfrith. There's a soil-based model, CSCM, and here this is the Kyrgyzstan in case. Look at the amount of parameters. It's like endless, goes on and on and on. Most of them are 0, right? This is all I know with certainty is my concrete strength. This is a uniaxial tensile strength. I can get the uniaxial compressive strength. The rest I have to guess. This is the uniform weight. This is the conversion factor, sorry. And then somebody here, Mutturaj, was presenting on load rate. So you can define the load rate, or it sort of represents in a way the dynamic factors. But how do you incorporate that, right? That curve you need to be accurately defining. So what they would do is they might have conducted some kind of tests and calibrated, let's say, all these models is calibrated to that test. So if I just use those values directly, I'm blindly using what they have given and proceed. This is very difficult to, time consuming, and whether it's worth it to develop material parameters even for this model, let's say UHPC you want to do, then you have to find out all the material parameters relevant, and that will be in addition to the database. And then what else? These are node definitions, these are section definitions and titles. Any questions? Many of you will be, see, that's why they have these load from databases. You can load some properties that exist. And then you have the dplot also, right, on this? Any questions on this? And then once you run it, it doesn't take very long to, this one is not very long, right, to run. So you can run LSDyna out here, and then once it runs it, there are things you can output. Let me mention a little bit of that. Here, the output, it comes in the database here. So look into, if you're doing database, look into all the different options. Typically it's D3 plot. There is also BLAST, BLST FORs that can be output for certain cases. It doesn't work for all situations. So more BLAST related parameters can be, so put some time there. Then once you run it, you have the D3 plot. It opens up Abacus. It may be a little different. It will open up something like this, and then you can run your, you can do either fringe plots or you can do history plots, time history plots. For instance, if you want to get the element and you want to get the effective stress on that element, just pick an element and so it plots the effective stress versus time. Here I have simulated for 30 milliseconds, I think. And you can cross check. One good way to maybe start a model, if you're working, let's say, as he presented with UHPC, you might have stress strain curves. So you can model the cylinder, maybe the cylinder that he did, and then match the curves. Then you can adjust the parameters to match the curves, and you can use that. That's one way I've used for high strength concrete. And then you can run, for example, you want to check whatever your, this is where knowing plasticity helps, because then you know which parameter to check, whether you want a strain parameter, what is the, are you interested in the effective plastic strain. There are non-defined NDVs. So let's say you want the von Mises stress, which is the most commonly used one. First principle and second principle is also used, and you can, based on the fringe, so it will show you some nice, I mean, you can change, for some reason, I don't know why it's not coming up here. For some reason it's not coming up. It's showing the, okay, maybe, but you get what I'm saying, right? You can get the pressure, whatever parameters you can get those. Usually those are not of that great interest other than you want to show where the high stress regions are, or you kind of want to simulate cracked regions and show the high stress regions. You can adjust your effective stress ranges and then show peak. Otherwise, these are visually good. History plots are often more useful than others. Do you want to add anything to it, Rauf? Or again, this is more not like a teaching presentation, but more to give you ideas again from UFCs and finite elements both. So, this was the response of reinforced concrete structures subjected to combined blast and fragment impact. So, a lot of, you see how if you are building up your research approach in this area, or especially this area, you have a literature review, then you try to develop a semi-analytical approach, then you want to try UHPC, for example. I'm using that because we didn't do that, but I'm using that because we had a presentation on it. Then you work on parametric or probabilistic, as Professor Ragappan was saying, and those are, and then you can develop GUIs or programs, as we had mentioned, somebody was asking during the break. But what is involved in cased explosives, different types of bombs are there, and yesterday also I think you showed one of, which one was it? The middle one, right? So, here are some details. If this is something I don't think I'll share for now, but have a look at it and you can take down notes. Well, the problem here is you have pipe bombs, very crudely made pressure cooker bombs. These have all been used for combined blast, and now energies is expended in breaking it up, and then there is free explosive. When it breaks up, the things you are interested in is what is the mass distribution or the particle size or the mass size, just mass distribution of the fragments that are generated. The fragments generated will have certain velocities. So, you are interested in predicting the velocities or maybe a velocity distribution, because you need from that an impulse distribution, mass times velocity. That is the, so the fragments come and there are two things happening. There is a blast pressure, and then there is also impulse that is being hit. We have seen those principles, impulse, momentum, they eventually result in work done. But so predicting that can be a huge challenge, right? And the shape of the casing makes a difference. Is it a spherical casing? Is it a circular, cylindrical facing this way, or is it facing this way? Orientation of the casings make a difference in how it impacts the surface there. And other, one more thing I wanted to mention, it's okay. Now, yeah, what matters is, do the fragments come first, or what damage the structure has had due to the blast, because when the fragments come and hit, is it hitting a solid structure or it is hitting an already damaged structure. So, the stiffness properties will change. So, we looked at, here is a brief literature review starting from 83, and you see if just a few people work, a lot more, maybe the group here in Israel, they have started looking at it from 2018 onwards, and way back when there are a couple of people who have looked at it. So, fragment inflicted damage, charged explosive, we see it has damaging capabilities and it is synergistic, the synergy between impact and damage, impact and blast. Then fragment damage is treated in a simplified manner in all these documents, or not treated at all, just a line saying consider it. And there are clearly lack of both analytical and semi-analytical models, and definitely this work was focused on the grade type of constitutive materials and identifying parameters that have influences. So, that is what it was to develop and validate for known existing work and then extrapolate. Part 3 is extrapolating to high strength. If you are not able to test, then you can extrapolate it. If you are having some tests, you can try it for that and then study the parameters. So, in the theoretical formulation, so you have the shock wave, you have the fragments, it can have global. So, the global effects is it has a response due to the impacts, we have studied that. Local effects is penetration, these are projectiles and you have seen that it has penetration, depth of penetration, damage, spalling, other such complicated effects, combined effects. Then the global effects is the structural response and we have looked at what defining spalling, breaching, etc. So, the adopted methodology was loading, then determining the fragment momentum, then the damage due to the momentum and then the response due to all three effects. So, luckily for you, UFC does have some equations. This is for blast loading. I won't spend time on that. You have done a lot of work on this over the last 10 days. But in terms of cased explosives, it matters as to where the detonation is, how high it is from the ground surface, where the detonation point is. That also makes a difference. The device, even if it is oriented this way, the geometry of the device makes a difference. And then based on the location, there is something called a Taylor angle, but the angle covered, if that makes also a difference. So, here you have, this is a free burst type detonation and so that is, and then this at the bottom you have the surface or the ground burst. So, surface burst. Then, so here you have it in terms of the net mass. There are some parameters it gives. I don't know why I can get rid of, maybe, let's see. So, there are equations based on, again, old, what you call reference, old work, that gives you the number of fragments here based on the weight of the casing and a constant MA, and it gives you the average weight of the fragment striking the panel. So, given these two, you can find and then the velocities can be calculated based on the weight of the charge and the casing, and here there is a constant called the Gurney energy constant. Based on that, the total momentum can be calculated. And then you have experiments due to fragment induced damage that we have studied. Then you have the penetration equations exist for the depth of penetration. This is the depth of penetration and the cratering also. You can how deep, what are the crater diameters, approximations of cratering. These equations are also there, we have looked at that. And then based on that, this is something called the fiber element method, where you break down the cross section into multiple fibers and each fiber has its own properties based on the actual cross section. And then based on the stresses on each of those, using some assumptions for steel and concrete, start with your strain displacement, strain compatibility diagrams. The other thing, we assume that the strain compatibility diagram is linear. When you do actual testing and place strain gauges are different, you may not find it linear, but those assumptions are made. And then you can calculate the axial force and the moments, and then using the material, and here you can incorporate rate models, strain rate models also. You can predict sort of the global response, either the P delta in the elastic phase or the plastic phase. And then you can develop these slab models. You have seen right now what are the different things. Now we have to incorporate, apart from blast loading, in the finite element models, you can incorporate the velocities and the mass of the fragments as impact loading. And then we compared the relative displacements separately, fragment loading, peak loading, and the combined loading. So, and these were compared with experiments. So, and that's how we did some damage. Once that validations are made, then you can try for different casing lengths, diameters, and do some predictions based on that. So, just wanted to give you an idea. I think there are more, but this is not a presentation, but approaches are there for, if cased explosives are quite common also. So, you have alternatives that you can look up in the UFCs, or we have these publications there, three publications. One of them is a review paper. That's a really nice one you should look at if you're interested in this type of work. I think I'm going to stop with this one because, I mean, our goal here is not to present these research results. But I think if you're interested, you can look into, because you have different concrete you're looking at, not necessarily casing, but approaches, right? How to approach and proceed with it.